Welcome back to PEEPanEIP, a video series and podcast dedicated to Ethereum standards and implementation. This is episode 128, and I'm your host, Pooja Ranjan. In the next few minutes, we'll deep dive into a proposal which is already CFI'd for Ethereum's next planned network upgrade, which is called as Pectra. EIP-7002 execution layer triggerable exit is a standard track code proposal and is in draft status. That has been already added to EIP-7600, which is hard fork meta for Pectra. To provide an overview, to talk about motivation, specs, and implementation status of this proposal, we are joined by Danny Rayan. Welcome, Danny.
Hello, thanks for having me.
Danny is a researcher and developer at Ethereum Foundation. He has authored multiple proposals in the past, and EIP-7002 is one of the best documented proposals I have came across so far. It's great to have you back again, Danny. I know if people are following PEEPanEIP or Ethereum in general, they will agree that you don't need an introduction. Yet as a format of this show and to encourage potential new listeners and followers, may you please briefly share a little bit about yourself before we get into the proposal?
Absolutely. Well, first of all, I can't believe you've done 128 of these. I've done 130 ACDCs, all Credential consensus layer call, and I was like, that's a lot, but this takes a lot more work. So respect. Cool. My name is Danny Rayan. I work with the Ethereum Foundation. I've been with the Ethereum Foundation since the beginning of 2018. I do research, specification writing, and then like some coordination around upgrades and things. For many years, I worked very deeply on proof of stake research and proof of stake specifications, which became the phase 0 beacon chain and then became kind of the backbone of the merge. And so often my work these days are thinking about security and feature improvements to the beacon chain because I have the spec very deep in my head. So it's not too bad to iterate on. I'll note that Mikhail and I kind of did some of the foundational work as co-authors. Then when we introduced the fee mechanism into place, which we'll talk about, Ansgar jumped in as he's kind of 1559 style kind of fee mechanism expert. Hsiao jumped in as a co-author when we started doing a lot more of the consensus layer nitty-gritty specs, and then Light Client did jump in as well when we modified some of the work to be EVM bytecode, which we'll get into all that, but just shout out to all these people. A lot of people have worked on it. And thanks. I like to pre-justify everything a lot in these specifications so that, I don't have to tell people 10 times when they ask me. All right.
That's a great overview, introduction about this proposal as well. So without further ado, let's peep in.
So generally, let's talk about the problem first. So since phase 0, since the genesis of the beacon chain now is the proof of stake consensus for Ethereum. There is this validator object, this notion of a consensus entity, somebody that puts up 32 ETH and takes on responsibilities and can potentially earn some ETH or potentially lose some ETH depending on how they do there. There's a number of fields on this validator record. Think of it as like a very special account in the beacon chain. There's firstly the two things we're going to look at here. There's a bunch of stuff like balance and all that kind of stuff, but we're going to look at the Pubkey, which we often call the active key, and the withdrawal credentials. The Pubkey, this active key, is involved in active validation. So it's a cryptographic key. You can sign messages to essentially like prove it's your identity, and you're saying certain things as a validator, like sign a block, sign an attestation, or these types of things. And it's live, it's hot, meaning it's like on a live computer, or it's in like some sort of hardware security module, but essentially it needs to be able to do things very actively. So it's like very high risk key. And so to balance out that high risk, there's also this withdrawal credentials. Withdrawal credentials can be cold, meaning you might need it every once in a while to like do an exit or to like do a withdrawal or whatever, but you don't generally need to keep it hot or live. You can like keep it in a super secure place. It can be a multi-sig, all sorts of stuff. And so the split allows for better security story when a user has to have the talk key. But in this relationship, the withdrawal credentials ultimately own the funds. They ultimately are where the money goes at the end of the day, and they get to say like, and so if your active key is compromised, you're still fine if your withdrawal credentials. But only the active key can make an exit. So only the active key can actually get that initial 32 ETH that can say I'm done and pull it all out, which is kind of degenerate. And I would even say it was a bug. And it's like kind of pretty serious oversight, honestly, from phase 0. This has a number of implications. It's a core custody story for sole operators. So if you own the active key and the withdrawal credentials, but if you lose your active key, even though you own the withdrawal credentials, which supposedly owns all the funds, you can't actually send that exit. So you can't actually get your money out by money ending. So that's bad. It's strange for the thing that's presumably ultimately owns the funds to not be able to signal these exits. There are trust issues. Because there are these two keys, there are a lot of more sophisticated custody relationships where one party might actually own the withdrawal credentials, and the other party might be providing a service to them where they own the active key and they're doing the live validation. But then you have this weird thing where maybe your ETH can be held hostage. Like this entity that was supposed to be validating for you, if you wanted to exit, they could say, "Oh, you can't force me to. Why don't you pay me? Or you can't force me to. I'm not going to listen to you." And then for this trust issue, there's a lot of bad workarounds, clunky workarounds at least. You can do pre-signed exits. So maybe that active key that someone else holds will pre-sign these exit messages and give them to me. Or if it's some sort of pooled solution, then maybe they'll give them to a committee. And the committee, for example, for some of these on-chain pools like Lido and others, like they have these pre-signed exits as different operators, and they have a separate committee that holds them. And in the event that they need to send an exit to a validator, they essentially then have to call in the committee. And there's like all sorts of complexity and trust issues with this. And so it's certainly worth solving. I'll make a note. Like you might say, well, maybe in this world where we have like problems with like super large pools and stuff, why do we want to actually make things better for them? And the answer is actually, if you're Lido or you're one of these very large operators and pools, you probably can afford to have a committee. You can pay them. You have trust. You have all sorts of stuff. Whereas like bootstrapping a competitor, if you have to have a committee to hold these pre-signed exits and stuff, like that's a moderately high, if not very high, barrier to entry to enter into the game. So leveling the playing field is very important here. I will note with the Dankun upgrade that went live a couple weeks ago, EIP-7002 did make this user story a bit better with this EIP perpetually valid signed voluntary exits. Essentially, voluntary exits, every time there's an upgrade, there's a version number increment on the beacon chain, which kind of like, and messages are valid from the current and the previous version number. So after a couple of version numbers ago, your pre-signed exits would no longer work. So then you have this thing where when an upgrade's coming up, you have to get the operators to pre-sign new exits and send them to you. Otherwise, you send the old exits and get out of validation. And there's a whole just dance that people do. This made the dance better, but didn't get rid of the dance entirely. Okay. So we have this problem. The problem essentially is that the ultimate owner of the funds can't send an exit. Exiting is very important for a number of reasons. So the solution in the abstract, the solution is to allow withdrawal credentials to trustlessly control the destiny of staking. Like the withdrawal credential should be able to submit an exit, and thus EIP-7002 tries to find a simple enough and secure way to do so. Note, EIP-7002 only allows 0x01 withdrawal credentials to send such a message, but this allows all validators to do so because 0x00 withdrawal credentials can morph into 0x01 with a one-time change message. Just for some background, 0x00 is a bit vestigial around the way the beacon chain was formed at the beginning. These are BLS key withdrawal credentials. 0x01 are execution layer withdrawal credentials, so there can be EOAs or smart contracts. And ultimately most validators, to ultimately withdraw your funds, you have to morph your 000 into 001. And if you wanted to be able to trigger these exits and you had 000 still, you would just do the one-time morph message, then you would trigger it from your new address. So it ultimately opens up all validators to be able to do exits with their withdrawal credentials. And this does so in a form by sending a message from the execution layer into the consensus layer to trigger an exit. This logically looks very similar once it makes it onto the beacon chain to the voluntary exit message that exists on the beacon chain today. But it does not deprecate that. So you can still exit with the active key, but this allows an additional exit method from the withdrawal credentials. So we're going to get into talk about very high level, then we're going to open up the specs and take a look at what it looks like underneath the hood. Essentially, there's three main components to this EIP. There is a system contract deployed into the EVM that has a place for users to make these exit calls in which they pay a fee and are inserted into a queue. And then there's a system call where at the end of the block, some system level operations happen and clean up some stuff within the contract and to queue the exits. Then there's cross-layer messaging that happens via the insertion of these messages into the execution layer payload block body, which is kind of that classic block. And these messages are in the form of a new operation, which the consensus layer processes the execution layer exit, which looks a lot like the voluntary exit. Let's make sure. Cool. So we're going to take a look at these handful of things here. You can still see my screen, right? So the first thing we're going to look at is the system level contract. Let's go. So when this was initially written, kind of implied earlier, we wrote it as a stateful precompile, where the logic was kind of specified, but not actually encoded in EVM bytecode. With EIP 4788, the beacon root opcode, there was a decision to not really go this stateful precompile path in general, and instead deploy these system contracts. So to conform to what is essentially kind of a new design standard, this was updated to actually be EVM bytecode, as you can see with this assembly right here. So there are two primary things going on inside the EVM bytecode. And we'll call this the validator exit contract. Essentially, there's logic to trigger an exit, and then there's logic to do system processing. So this is pseudocode, or maybe it's actually Solidity. No, I think it's pseudocode. So it represents the logic, but the ultimate definition of what happens is in this assembly, which we're not going to go over the fine-tooth comb today. We'll look at the higher level stuff. So we looked at these, these bullets right here mapped to these comments here. So first we want to verify that a sufficient fee was provided. Then we want to increment the exit count, which is the variable inside the contract. And then we want to insert the exit into the queue. First of all, we actually haven't talked much about this fee. There is a fee paid to this contract, essentially in the form of a system level burn to produce one of these exits. This is to bound the this is to prevent griefing of making a bunch of like validator exits to get that ultimately would be invalid in front of users that might want to get valid exits on. There's a few things here. The execution layer, this contract, the execution layer now does know about the consensus layer because of 4788. You can make proofs about it. But this contract doesn't want to rely upon those dependencies. This contract wants to be able to work in isolation. So this contract doesn't know anything about the consensus layer. It doesn't know anything about the state of validators, doesn't know what their pub keys are, their balances, anything like that. So it can't really do any validation of whether these exit messages are correct. And so instead of trying to insert validation logic here, which would be quite complex and quite brittle if there were subsequent upgrades, what this does is it uses an economic mechanism for rate limiting. Essentially, it's very similar to 1559 style mechanism where the more exits that are made to this contract, the more the exit fee, equivalent to kind of like the base fee in 1559, increases into an exponential level. And so spamming this quickly becomes uneconomic. And so that is the mechanism to prevent someone being able to dump, 10,000 in here and prevent validator exits for a long time. So there's this fee. What we do here when we're going to trigger an exit, I make an EVM call to this contract. I make sure that enough fee was passed in here. This can be read via a public interface. I increment the exit count, which is utilized in calculating the fee and handling the queue logic. And I insert this validator, I insert these fields into the queue. And the fields are the source address and the public key. So who called this and what validator public key are they attempting to withdraw? The source address, well, ultimately, when these things are valuable because the pub key uniquely identifies the validator, and the source address should map to their withdrawal credentials. If it doesn't, then it won't be valid, and we can look at that in a minute. So that's simply what's happening here. Is we're managing a queue, we're paying a fee, and so this queue can grow throughout the block. And validators can be added to whatever extent that this call is being made in normal user transactions. Ultimately, the amount that can be made is bound by throughout the block. Users can make exits, they pay a fee, they get in the queue. At the end of the block, there's the system operation. So we're done with user level transactions. And now we're kind of like doing various cleanups. This is the same time that like the Coinbase is going to be rewarded and other just like general cleanups and operations around the execution of the block might happen. And what this does is there's two entry points into this contract. If you're the system address, you go into read exits. If you're not, you go into this generate exit function. And so there's like kind of a artificial call, not out of a user transaction, but just from the system, made from the system address to this contract at the end of the block. And it routes into this read exits function. And the purpose here is to pull off the oldest up to 16 exits. That's the parameter in here, and it's 16. Remove them from the queue, so actual state change. Update the excess exits, which is a calculation in relation to that fee, and reset the exit count for that block back to 0. So dequeuing the exits, if I have 100 exits, I take the 16 at the beginning, I pull them out, I move a pointer so that the beginning is now at the end of those 16. And then excess exits, I'm not going to get too much into how this like exponential fee is calculated in here, but essentially we're tracking, there's a target number of exits per block. Right now it's specified as 2. And in the event that there are more than 2, we track that. And by tracking that allows us to know like, oh, there's been a lot of demand on here, so the base fee essentially needs to go up. In the normal case, we really expect there to be far fewer than 2 exits per block, and that for this fee to be 0 or essentially negligible. Only in like times of kind of crazy runs on exit or potential like someone trying to grief and create some sort of hack do we expect that to exceed that 2. 2, just for context, is 64 per epoch. I think there's some calculations below we can look at that help us justify that number. Okay, so at the end of the block, there's some system operation, and we get up to 16 exits out of this. And these exits, if I'm the block producer, I put them into the execution payload, and I sign it, and that's part of the data structure. If I'm a block verifier, which every node verifies all of these logic of the block, I pull those out and I make sure that those, in fact, the ones either 0 or up to 16 are in fact the ones that were in my execution payload. And if not, then I block's invalid. So this becomes a block validity condition where the correct exits that were triggered in the execution layer dequeued from this contract and placed into the block. And so what we were doing So this is the actual bytecode. Matt is a bit of a bytecode whiz, and hopefully, if you're watching this and you like assembly, please audit this. Well, this is very important to get right. It's written once. It's deployed for all, into the EVM. It's a system level contract. We're going to do a lot of like manual verification here and have some audits, but if you want to jump in, this is a great place to help out. So as I've said, these are dequeued from this contract into the execution payload, the block body, and their structure essentially is this exit structure, which, as we looked at, are those two fields, the source address and that pub key. The pub key being a validator pub key. So here we go. That's generally what's happening here on the execution layer. This is now a validity condition. You now have the ability to send normal user transactions to make these exits. And now that putting it in the block body allows you to hoist it into the consensus layer. You might ask a question. Why do we actually have to put it in the block body when like you could potentially just like read, you can just read the consensus layer should just be able to read the execution layer. And there's a fundamental design constraint on all these kind of cross-layer EIPs, cross-layer meaning consensus layer to execution layer, and we want them to be able to be executed in parallel. We want, and they want to be able to be executed independent of the other. Meaning, if my execution layer was offline, I should still be able to validate and operate the consensus layer half of the thing, and vice versa. If I'm executing, execution layer transaction, execution layer payload in isolation, I shouldn't have any other dependencies. And so by putting it into the block body, I now achieve that. I get that, like I can parallelize because I don't have to wait until the end. Notice this happens at the end of the execution layer execution. And in the event that my execution layer is offline, which maybe it's syncing or there's all sorts of reasons that might be the case, I can fully validate the consensus layer portions of it. And so this is a technique, and it has been used in a couple of EIPs, like for example, with withdrawals, and will be used in probably future EIPs. Essentially, these like pieces of information that have to get passed between the layers are placed explicitly into the block, rather than just like rather than just dynamically having the software pass it back and forth. Cool. So the next component is the consensus layer. Obviously, or maybe not obviously, with the consensus layer, we have a kind of a rich specification of this like Python executable code that we rely on for specification and for building, testing and building tests and stuff. It's really great. And that's now linked into the EIPs. So we might flesh this out a bit, but right now what we see is just kind of a sketch of what's happening in the consensus layer. Essentially, we have a new operation. The word operation is essentially a validator transaction. Early on, we decided to kind of separate that namespace between user transactions and validator operations. Validator operations, include like deposits, exits, attestations, a very constrained set of things. So we get a new operation, the execution layer exit. The consensus layer has view into that execution payload, so it can grab these new exits from that payload that was added here. And we have a new function that we take all of these and we process them. And that function looks very similar to process voluntary exit with a very important asterisk. And at each block, we call this new function for all of these operations that are found on the payload. So let's take a look. This document is essentially the diff that EIP-7002 puts on the beacon chain. We get this data structure. This is that same data structure that we were just talking about, the source address from the EVM that triggered the exit and the validator pubkey. We get a modified execution payload, which is essentially that execution layer block to support these exits within it. It modifies the header, which essentially is that list, but just with the root. Doesn't matter too much. And then in the beacon state, this is more just procedural. So as I said, we get this new function. This is kind of this is really the core right here. Is for each of these exits that ends up in that execution payload, we need to call this function on it. And that is this function, process execution layer exit. This looks almost exactly like process voluntary exit, but with one very crucial difference is that all of these are return values, meaning they're not assertions. In process voluntary exit, if your validator has already exited, and that message is included on chain, essentially it throws an error and invalidates the whole block. So, but none of these conditions, is it an active validator? None of those conditions did we validate in the EVM, because remember, we just used kind of like that economic rate limiting, and we didn't bring in actual validation logic against the consensus layer. So these messages are not validated. So these messages were forced to be included. So these messages cannot invalidate the block. Essentially, if there's something invalid about them, they just need to be a no-op. And so that's what's happening here is normally, like in process voluntary exit, we see very similar conditions, like is the current epoch greater than the exit epoch, but we see an assertion, which fails the block. Whereas here, we're just like, silently just exit with this return value. And that's because of this like inability to pre-validate. But we still get the rate limiting on these messages from that feed. Okay, so back to here, we're doing a few things. One, we need to make sure that it's authenticated. And that's what's happening here. Is did the withdrawal credentials actually send this message? And so we check that here. We want to make sure the validator is active. You can't exit a non-activated or already exited validator. We want to make sure that no exit has already been initiated, because you can be in the exit queue as a validator, but not quite exited yet. So already attempted to be exited, but still kind of going through the process. And this is a bit vestigial. The intended sharding design has changed quite a bit since phase 0, but essentially, I think this is 256 epochs is about a day. You have to have been active for at least a day before you can get one of these messages on chain. And at that point, we initiate the validator exit. This mutates the state by updating some of the parameters in the validator, and that's that. Let's see. I had a couple more things I wanted to look at. All right, cool. Let's take a look at the rationale and just make sure that we covered all the high points before we open up the questions. This is interesting, and as I read this, I realized it needs to be expanded upon. But we need to disambiguate why the validator Pubkey field. We need to disambiguate which validator is being triggered in exit. And you might say, well, what about the withdrawal credentials? Why can't we just use that? Well, many validators can use, and in fact do, use the same withdrawal credentials. For example, if you're a home staker with 3 validators, you might use the same withdrawal credentials for all of those validators so that any withdrawals and stuff go into the same place. Similarly, pools often use the same credentials and stuff. So then you say, okay, well, why Pubkey, which is unique, instead of validator index? We use validator index all over the place in the consensus layer. Well, that's an interesting one. The consensus layer knows deeply natively about validator index, but the execution layer does not. And so say you're an on-chain pool and you're submitting a new validator, you're making a new deposit. You know the pub key that you're making deposit for, but until it goes through the deposit queue and actually makes it onto the consensus layer and creates a new validator object, you don't actually know the validator index. And so the execution layer natively knows about pub keys at the point of deposit, but it really doesn't know about validator index. You can now know because of 4788, but that you have to make like proofs and do all sorts of complexity. That's not really worthwhile to do so when the pub key works really well. Why an exit message queue? We talked about this a bit. Essentially, we want to rate limit the number of exits that need to be processed per block on the consensus layer. And so we shove them into the EVM state to be dequeued at a very reasonable rate. The amount that can enter the queue is only bound by the gas limit. We don't really have that notion here, so we do allow them to be bound by the gas limit, but then we queue them up until we want to send them to the consensus layer. This is wrong. I realize this contract doesn't currently return excess payment. This needs to be removed and reworked. And then rate limiting using an exit fee. We talked about that moderately. Essentially, we're not doing any validity checking, whether these messages are going to make it. So instead of validity checking, we're using an economic rate using that exit fee. We expect in the normal case for this to be 0. And only in exceptional cases for that to climb in that exponential way. It's really much more of a griefing vector protection than an expectation that tons of exits are being made all the time. We're doing 16 of these exits per block. This is exactly the number of voluntary exits that can be included in a beacon chain block. This is roughly in the order of magnitude of other similar operations. And so what we get here is a bound on the complexity of the number of signatures and kind of processing that needs to happen. Exit fee update rule. I'm not going to get too much into that. Ansgar, one, this is Ansgar's baby. Two, I think the intuition here is essentially that the exit fee does increase exponentially as there is, if in the event that there's more than 2 per block, and that rapidly then decreases again, essentially to protect us from spam. And we talked extensively about why exits actually go into the block because of the parallel and independent processing. Questions? Oh, something I didn't actually state. I stated actually at the beginning. The 001 credentials can be EOAs or smart contracts. So a nice functionality here is that actually you can have arbitrary logic potentially trigger exits. So if you're building something like an Eigen Layer or something where you've premised upon this other logic, you actually want to be able to trigger an exit, you can now kind of program arbitrary stuff, which is really cool and terrifying at the same level. So
thank you, Danny. It was a great talk, and as I was mentioning in the beginning, the EIP documentation, it contains a lot of information, and the proposal is still in draft, so there's plenty of room for edits before it is added to the devnet. You can definitely edit it even more, add more information wherever needed. And yeah, I have always liked the idea of Ethereum developers planning in advance. Like it was a news to me, and I'm very happy to know about it. Like 7044 already deployed with Dencon helps this proposal as well. Yeah.
Yeah, 7044 improves the existing user story. Without, in the event that this never went in, things are a little bit better with that. This makes it much better though.
That's great to know. I mean, I should have paid a little bit more attention when we had this conversation with Daplayan, but yeah, glad to know that. I think this is another cross-layer proposal for Pectra Upgrade, which would be like obviously require input from both sides of developers,
Right.
7002 and 6110. Yeah, these two are the proposals. I think they did not receive a lot of argument. Developers did not debate it much. They just said, yeah, let's get these two into the upgrade.
Yeah, I mean, in both of those, it just seems very much like there's something broken and this is the way to fix it. It's time to fix it, right? Like merge done, withdrawals are done, 444 is done. Like there's a couple of like pretty obvious wins. And it was nice to see everyone rally around those. When things are kind of more fundamentally security related, often you see people get to the no-brainer level on inclusion quickly.
Right. Yeah. I mean, like my first question was around that. Like at the time of documentation, were you confident that it will get an easy pass as it did 6110, or will not end up as 3074 or something like that?
Oh, sorry. What was the question is, how do we know?
Yeah.
I don't know. I mean, the closer it is to the core mechanism and security around the core mechanism rather than user land, the more the closer the more things become a bit more of a no-brainer. Whereas I'd say the more we get into improvements, even security improvements and changes to user land and how users operate and interact with Ethereum, the tougher things can be. I think that the more there's a diversity of opinion, the more it's not clear, the impact on security. Whereas when it's touches like this more kind of isolated, the core of the mechanism, a bit more straightforward. Usually we're debating like subtleties, like do you do it this way or do you do it that way, rather than like fundamental, should you do it at all?
Usually it's a little bit challenging to get all client teams on board for any proposal, but you managed to get 2 layers client team to get this proposal in.
I honestly was a bit surprised, but I'm happy.
Same here. Well, you already explained many reasons for having this proposal in place. You talked about complexities and trust issues. I'm curious, was it always there in back of the mind since we started withdrawal, or what was the main inspiration behind the creation of this proposal?
I don't remember exactly when, but the beacon chain went live at the end of 2020, and pretty quickly when we started seeing more advanced custodying, like people, a centralized pool custodying for validator or for people, capital holders, or seeing some of these like on-chain pools, it just became very quickly clear, like it was just a deep oversight to have only the active credential be able to do the exit. I mean, honestly, like phase zero was huge by many respects, and a lot was done, I think, really well, and the system worked exceedingly well. But only when we really actually had users, had validators, did this just show up as an issue. And like I said at the beginning, I think I would just call this a bug. Like it was a specification bug. It was incorrect. Like it was just deeply an oversight. And so there's been a hope and notion to kind of change that. But once the merge happened, it became much more obvious the right way to do it.
Right. I remember when people were talking about withdrawal after the merge, there were multiple proposals up. One was like push proposal, one was like pull proposal. 4895 was, I think, push proposal, and there was another proposal for pull that was again supported by 4788, which you mentioned in your presentation as well. At the time, people agreed with push design, and 4895 was deployed. Do you think this is kind of like bridging the gap that we could not get the pull one in?
Meaning, does this have a relationship to the pull design?
That's right. Or with any relationship with 4895 at all?
Yeah, it's relatively independent. Like we think about, there's two different things going on here. There's exits, like I want to stop validation, and then there's withdrawals. I want to withdraw my capital. And push versus pull was really only kind of a design nuance and different ways to do it on the actual withdrawals. Like once somebody's exited or the capital is ready to come back into the execution layer into a user account, how does that happen? How does someone initiate that? Whereas this is one step upstream, which is how do I actually just exit and say I don't want to be a validator anymore? There's certainly like design principles from the withdrawals that we've taken and learned here, and one of the very obvious ones is using the actual execution payload as a messaging bus, like putting these messages explicitly in there to allow for that parallelization independent execution. But other than that, I'd say they're relatively independent. This doesn't necessarily have much to do with the push versus pull.
Great. Good to know that. I'm just trying to understand a little bit more about it in terms of operation. So it's just that it is a process level and it talks a lot about fees and everything else. So can you share why 7002 is a process level operation and not a system level operation? I mean, if you can maybe add a little bit more about what is the main difference between process and system level operation, that would even help to understand it even better.
Right. Okay. So there's this contract, and this contract has a couple of functions on it, and it has state. And so I don't know if I exactly understand the question, but we have users send normal transactions to hit one of these functions, and that's to trigger an exit. And that mutates the state. That helps. That's where they pay the fee, and they go through that. Whereas at the end of the block, there's another function, but it can only be entered into by this like strange system address that you couldn't actually trigger as a user, and that's like 0xFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFF. At the tail end of the block and at the beginning, the system does like a few things. It does some bookkeeping, does some checks, might increment a number here or there. The example I like to use is Coinbase. Essentially, like all of the user transaction fees that were paid to the Coinbase opcode go into that account. So like a state transition happens there. But essentially, like the second function, which reads the exits and does some validation, is called more in kind of a system context. It's not in that normal transaction execution of blocks. So there's kind of two modes in which this contract operates, and it's normal user transactions and then like a system cleanup operation at the end. There was a design, maybe another component here is there was a design before 4788 went live that would essentially do a stateful precompile and not actually embed this as bytecode, EVM bytecode, and just embed this instead as like specified logic. That route was not taken in favor of this kind of bytecode route. Sorry if that didn't answer the question.
No, that helped me pretty much. So yeah, thank you for that. My next question is about exit messages queue. So we know that there is a cap or limitation to exit messages per block. Will you talk how 7002 fit there, or maybe does it change anything with the present exit message queue?
So in the existing beacon chain, we have voluntary exits. There's no queue. There's a mempool. So I broadcast, if I want to do a voluntary exit, I broadcast it to the network. It hopefully gets picked up in a block. 16 of those can be added per block. And that's all in the consensus layer. That has nothing to do with 7002. In 7002, we want a similar rate limit on the consensus layer. We want 16 or something in that range. It's currently specified as 16 for these execution layer exits. Given that there's no validation of the validity of these execution layer exits in the EVM, we essentially want to like collect them in the EVM and then only send them maximum 16 at a time per block into the consensus layer. So that's what this queue does. This queue, there's a natural rate limiting of how many of these can be triggered in the execution layer per block, and that's the block gas limit. And that number has presumably been safely selected in relation to gas costs, and so it can handle 30 million gas of exits. We're probably never going to see 30 million gas of exits unless some crazy unexpected scenario. But those then land in the queue. And however many of them land in the queue. And then at each block, to rate limit the consensus layer into that 16 is when we pull off 16 per block. And so the queue could grow and be like 1,000 long, or we'll call it 1,600 long, and it's going to take 100 blocks to dequeue them into the execution layer. These parameters have been chosen, though, with that target of 2, such that there's all exits will be processed. In relation to that exponential fee, you can't actually spam there to be more exits into this queue than could ever be processed in relation to the burning all ETH in existence and the other set size. That's what the queue does. Essentially, like the gas limit bounds user activity. User activity can be triggering these exits. That activity could exceed what we safely want to put into the consensus layer each block. So instead of shoving them all into the consensus layer each block, we put them in EVM state queue, and then the system pulls them out and safe limit at each block.
That's great. Somehow related question about the fee calculation that is added in the proposal. So this particular section, is it to maybe help adoption, or like let the user know that this could be really beneficial for you to adopt, or is it just for the developers, client developers, to make it clear why we are proposing this one?
This is the justification at the end, rate limiting using exit fee, or
the fee calculation, how to calculate the fees that has been explained in the proposal.
oh, okay. Yeah, I mean, if you look at the bytecode and you look at the pseudocode, it's just not very clear intuitively like what's going on with these like exponential calculation. So Ansgar took some time to just explain how this maps onto something that feels similar to 1559. You know, maybe one of the implications is like, would people be excited about adoption because of the way the fee burn works or something here? That at the target of 2 exits per block, only in exceedingly exceptional scenarios would this fee be non-zero. And so this isn't going to be like a source of like you know, a different level of kind of economic burn on Ethereum. But this is much more just about like explaining how this exponential works in a bit more human readable way than the pseudocode above.
These minor details that has been added to the proposal actually kind of excited me, that there's a lot of information which we generally don't find at any of the proposals. So thank you, the entire team, for adding bit by bit to it. One general question here is like, we talked about a lot of things, why it is needed, why it is important, and everything else. In general, do you have like some specific use cases in mind, like by which you think that projects would be inspired to get this adopted sooner rather than later? Or the validators will be
Yeah, I mean,
excited?
the most, I'm going to speak for the hobbyists. Like, this is a great, like, if you lose your active key, you don't want to have lost all your, you know, and it wouldn't be lost. It'd be stuck on the beacon chain. And like, eventually when you know, maybe decades, literally decades, once you hit the ejection balance, which is 16 ETH, you would get like half of it back or something. This really helps that user story. You know, first and foremost, that's like the major win here is to ensure that if you still have the key that owns the funds, you can get the funds back out. You know, and then the other two things are these more complex custody situations. Maybe you're using a centralized custody provider, and you keep the withdrawal credentials, they can't hold you hostage anymore. And then the third one really is, you know, there is a lot of like on-chain activity in relation to, you know, sophisticated validating setups, extending slashing conditions, like all sorts of stuff. And people are doing, like, it's not like this is going to make it happen or not. It happens, but then they require, you know, insecure committees and pre-signed exits and all kind of stuff to make it happen. So what this does is it lowers the barrier to entry to participate in that type of activity in terms of like the on-chain stuff, and it makes it safer. You know, um, it's a bit of a weird one, right? But it's certainly like, if you're writing a new on-chain pool or something and you can use this facility instead of having to like hack together some N of M committee construction to do this, then you're going to be in a much better shape. And you know, the user land in relation to all these weird validation things people are doing are going to be a much safer place.
So you mentioned that you would be talking on behalf of hobbyists and people who would want to do or implement it on their own. So talking about them or keeping them in mind, can we talk about any potential risk or challenges associated with this proposal to be implemented, if there are any?
Yeah. So anything cross layer is riskier than things in isolation. It takes more testing, there's more edge cases and things to think through. I certainly, the analog of this that's gone into production already is withdrawals, and the way that those work with kind of the messaging bus and stuff. So we do have good ability to test this and good ability to kind of get it right. But that increases the complexity always. And then in terms of like user interaction here, you know, if you had an EOA that was your withdrawal credentials and you lost it, you're already pwned today. So this doesn't really complicate that story. It might, obviously, anytime you open up a new programmable functionality, like with smart contracts that might trigger this, you're opening up, you know, unknown things that people are going to play with, and which is going to increase complexity of the smart contracts they deploy and potential risk profile on things. But I really think that that's a bit of a stretch, in that this is generally just like a security improvement. This is simplification in complex user stories that already existed today. Obviously, you can always shoot yourself in the foot, but I think this is a safer way to hopefully not shoot yourself in the foot.
I hope so too, because things are there to make your life simpler, not even complicated.
Right.
All right, talking about implementation, are you aware of the current state of client implementation for 7002? Because it has to be implemented on both sides. And
Yeah. Go on.
yeah, and do you think with the first devnet for Pectra, will that be included?
Yeah. So 6110 had a moderate amount of active R&D. It seemed like there were just more design questions to answer, and that active R&D with an EPF fellow or two was actually really valuable. There are fewer unknowns here. This is like, it's cross layer, so there's complexity there. It's pretty I call it like a bread and butter EIP. It's not like there's going to be tons of stuff to unsurface. So I'm not aware of any prototypes that exist yet today, but we're working on building this and a number of other EIPs that have been CFI'd into the Pectra spec, and we will have in relation to that an active set of test suites that come with it. And I don't think there's going to be much issue or complexity in getting this out. So I do expect it to be in the first wave of devnets, which we hope to see at the end of May. We'll see.
Right, there was a brief mention of the upcoming devnet. Let's hope to see 7002 over there.
Yeah.
All right. There was an article on 7002. The author is trying to explain the proposal, maybe for general audience, to provide them a good model for easier to understanding this proposal. And according to him, he proposes 7002 as a good mental model for 7002 is that you can think it of as an account abstraction for staking infrastructure. I'm curious, what are your thoughts? Would you consider this to be a very good analogy?
That's interesting. For a component of it. So what we do is especially because you can trigger these with smart contracts, the validation logic on what triggers an exit can be entirely, expanded. So account abstraction essentially is like, what can control my user account, or what can control account in the EVM, and you essentially open that up to arbitrary logic. And this is essentially what can control an exit of a validator. You could imagine like a much more extreme version of account abstraction for validators where like, you could sign an attestation with arbitrary logic instead of having to use your BLS key. You could sign a block with arbitrary logic instead of having to use your BLS key. That is not what this does. There's many reasons, probably security reasons, and also like practical engineering reasons. We love BLS aggregation, and so we like to be very opinionated about that key. But it does open up that account abstraction in relation to the exit, which is a very powerful, right? It's very powerful to be like, nope, I'm done. You're validated, you're out. And so it's like, it does get there, but there are versions of account abstraction for validators that you can imagine that would be even more heightened. But I like the analogy.
Yeah, and I think that if it somehow relates to that, that definitely opens a lot of door of opportunity for new smart contract developer to kind of make use of this proposal into different purposes and different projects.
Yeah, we'll see what cool and terrifying things people do with this.
Yes. We look forward to that. Very well. We are close to the time and it's almost time to wrap up. I remember you shared about taking some personal time off in the ACDC meeting. So while you're away, do you have any suggestions or recommendations on how community may continue supporting Ethereum research work or Ethereum development work in general? I mean, do you have any message for the Ethereum community?
I don't know. Y'all are going strong. I think this is really just, I'm gonna be out for 3 months. This is really just an exercise in proving to y'all that you don't need them, which has been the case for quite a long time. But yeah, Terrence, don't break it. Justin, don't break it. James, don't break it while I'm gone. And if you do, only call me if you really. But yeah, I don't know. I like. It's really exciting to see Pectra shape up. It's really exciting to see, all of the client diversity on the execution layer has greatly improved. Really, really fun. It's great to see what's going on with the blobs, and I'm really excited about, the PeerDOS R&D. I guess I'll give a shout out to that. Like, obviously, we're really planning for Pectra. PeerDOS is not going into Pectra, but it's going to be this kind of independent R&D thing. And quite frankly, there's a lot of work to do. We have a pretty clear path, but there's a lot of work to do, both in terms of prototyping, simulation, analysis, security work. And I think if you're into P2P stuff and you want to get involved in Ethereum, PeerDOS is a great place to get involved. Obviously, jump into the R&D Discord, work on some specifications, hit up the EF or some other grant giving body for a grant.
Well, thank you for this great message. I hope nothing is broken, but we still need you to come back soon. You have a great vacation.
Cool.
All right. Thank you so much, Danny Rayan, for joining us on PEEPanEIP and talking about upcoming changes with 7002. We look forward to see this proposal in the devnet, hopefully very soon, and on the mainnet when Pectra's date is decided. On this note, thank you everyone for watching this special episode on Pectra. All YouTube viewers and podcast subscriber, if you have questions, please drop them in comments. We look forward to answer those questions, and we would also love to hear some suggestions on what other topic that you would like us to be covered here in this PEEPanEIP series. We'll be back with another interesting talk. Until next time, keep watching, keep listening, and keep sharing your love with Ethereum cat herders.